So I will be talking about journey of TIFR in cosmic rays and particle colliders. So landmarks, and since I have to cover these two areas, so that's my landmark. And this is cosmic rays and non-accelerator-based particle physics experiment and particle physics at accelerator. And then I'll start with some statements about future. Now, with this cosmic rays, there are so many things that happen, and it's impossible for me to cover everything that will happen. So I will pick up some glimpses from here and there, and give you some idea what are the type of excitement we had in those days. So we start this exploratory work at KGF during the early 50s, moving to the mountain to extensive self studies at TIFR C block. I believe we came in. We had the rooftop occupied around the and KGF surface and underground areas with extensive work. Then we to KGF, digging deep underground and nothing is up to great depth. We found us in a non experiment, a neutron experiment, photon decay. And at the time when we were doing cosmic ray within the charged particle, there was also looking to the very active gas rays and start at 80 and into and 16 and we are participating in the milestone and David chamber experiment, then in full L3 experiment at CERN and BGD experiment at CERN. I will not be talking about the experiment that is going on at COVID, but I will make some statement at the end. So that's why I'm not including the ongoing experiment, CMS and others. Okay. So actually the journey of TIFR in experimental science started before TIFR was created, really speaking. And that started, and you know why I'm telling this statement. It started by Cosmic Ray Research Unit at Bangalore, where Homi Bhavan was located at that time. That's what I said, seeds of Cosmic Ray Research at TIFR were really strong, even before TIFR came into existence in 1945. And that's in 1943. Bhavan wanted to start cosmic ray experiment, and he was starving for data during the war. No data was there, he was not getting, so he started starting himself with this experiment. So he invited Miguel Sekar Sena. He was actually working that time with D.M. Bush at Bush Institute to build a cloud chamber. And MS Sena came to Bangalore and built a 12-inch circular cloud chamber, similar to the one that available at Brackett Lab at UK at that time, and Miguel Cosina happened to have worked with that cloud chamber. And later on, it so happened that Professor Sina was my teacher at my university days, but that's I only learned after coming here that he had built the first cloud chamber of TIFR. Anyway, so and then you did for the study of scattering properties of Melbourne, while in Bangalore itself, and of course, additional Odin was talking about in December 1945, he flew to a telescope with GM counters, sandwiched with lead plates using US plane stationed at Bangalore during the wartime. And the first measurement of high altitude measure intensities at exterior latitude was done by this one. So this was the activities that was going on. And when Bhava came from Bangalore to Bombay, he carried with him this 12-inch cloud chamber. That's what I said that TIFR started the experimental activities in Devon. As soon as this TIFR was established, actually started growing the field, and of course we had the cloud chamber, that circular cloud chamber 12-inch that was built there, but also expanded in other areas like GM counters, diagonal counters, and this is the glass growing section, and for the neighbor visiting, and the main purpose of glass growing section is to build actually this glass GM counters. That's one major job that they do, and of course that is this emulsion chamber, this photographic, developing lab where this emulsion developed and taken care of. So these are the activities with which TIFR started its journey at the beginning, and soon the first international conference on elementary particles in India that happened in TIFR in the old club in 1950, and many luminaries were present in that. And that's what actually talked out the future plan of cosmic ray research in TIFR. And one of the person that was attending that meeting was Bernard Peter. And as you know, and for next almost 8 to 10 years, he actually saved the cosmic ray research in TIFR in many areas actually. And this was I have picked up this role that I call it. These are the first set of leaders that led these activities in cosmic rays in India, in TIFR in particular. And I'm not going to talk about the work by all these people. And here is Homi Bhabha himself, and Bernard Peter, Biva Chaudhuri, Roy Daniel, Sukumar Bishwas, V.V. Srikantan, Yatpal, Devendra Lal, and M.G. K Menon, who came in 1955. And of course, these people actually are very interested in balloon-borne emulsion experiment, and that's what they are carrying on. And I will be talking about these diagonal lines, and Homi Bhabha, B.V. Srikantan, and M.G. K Menon, and their activities hereafter. So this is actually at that meeting at 1950, it was idea that you have to measure the, Bhabha was interested mostly in the cosmic penetrating component, because he has this cascade theory, and he wanted to understand whether there is only one penetrating particle or more than one. So he asked Srikantan to go to a polar gold field and at Bulandsapnir in KGF with the underground detector that I'm not showing here. These are the arrays of surface arrays here, and I can show you that much bigger how it looks like. And in a much many years later, and Kolar Goldfield again, a surface array, you can see all these arrays that are sampling the earth shower coming, and there are deep underground, and there are actually these buildings are also hosting the muon detector because there is a granite which will stop other particles to go through this detector. So these are the various activities over the years, and expertise developed, and new instrumentation built, and new expertise developed. One thing I must tell you here, that these scintillators were all built in India at BRC, and at that time TIFR could take the pride that they have the maximum area of scintillator detectors anywhere in the world at one time. So that was the type of development of instrumentation happening, along with science that was going on. Everything was developed locally, and because everything was developed locally simply the other reason, because not much foreign exchange was available in those days. So you have to build it from on. But this shows some ideas of what was going. And then many people have participated in this experiment. I'm just not going who participated in one. Here are the main name: Acharya, Chatterjee, Sunil Gupta, Siddheswar Lal, G.T. Murthy, Naranan, Raghavan, Ramanamurthy, Rangaswamy, Shiva Prasad, Srikantan, Srinivas Rao, and Subramaniam, Tonwar, Vacha, Vishwanath, and so on. So I hope I am not missing some. I think Srikant Rao's name is missing here, so, and participating. So now to give some additional expert, when they're making those air shower, they are also building some other detector to study the special characteristics of the air shower. For example, here, what you call the total absorption spectrometer is a marvelous thing they have built in 60s. Actually, sometimes I wonder they built that in 60s. If you look into carefully, what they wanted to study the core of the air shower, where many hadrons are going, their properties, what kind of particles they are, and how it is. So this detector, if you see, there is a combination of many detectors that you find in today's particle collider experiment at CERN or Fermilab, anywhere you go. At the top, what you call is the air Cherenkov detector. This air Cherenkov detector will separate out a pion from a proton and so on. So charge separation it will do. Below that, a cloud chamber was put. The cloud chamber will detail study of the hadron component. And finally, below that, what is called a scintillator iron layer, 20 layers of scintillators and iron plate to absorb the total energy. That's what you call calorimeter these days if you go to CERN or Fermilab. So this was in 60 built by our people here in India to study in details about those particles in those days. So this is the structure they have built, and the person who built this one, Ramanamurthy Subramaniam and Srikantan was the main person who built this whole detector, using, of course, the workshop at TIFR, using all the scientific people, technicians that we have trained and developed in the process. They are building this type of experiment. While this is the large cloud chamber, this is one time can take the pride of the biggest cloud chamber operational anywhere in the world. This size is 2 meter by 1 meter, 1.5 meter cloud chamber. It was in the mid 60s, used for many years in Uti, even when we were joined. Actually, when we went to Uti first in 1978, this was fully operational for hadron interaction studies. And here you can see the picture in that cloud chamber. The interaction taking place and shower developed and dying. And here is the penetrating longer moving shower. So many such pictures were taken, studied, and part of the earth shower at Uti. So this was and this one, of course, I should put this one. This was that time in the 60s. Professor Miyake came to India, and on the invitation of Professor Srikantan and Menon, and Miyake was an expert in cloud chamber, and he helped building this particular cloud chamber of that big actually. Well, these are the story about these things. Why this is going on at Uti, a new lease of life for the KGF activities, simply because the mines were closed in 1954. What happens is that government of Karnataka took over the running of the mine. So mine continues to running. So Ramanamurthy was in Bombay, and that time he was pressing that let's go back to KGF. We have left that job of measuring the muon intensity and only gone up to some 270 meters and so. So then KGF mine got a new lease life, and in 1956 it became Kolar Gold Mines Undertaking, and later by the government of India, Bharat Gold Mines Limited as a public sector undertaking, and it continued till for some more decades actually. So Gola Goldfield Laboratory restarted in 1960, and these are the people who started that. I mean, this is not their picture when they started that, and I mean they are much younger in those times when they started. Professor Menon, Srikantan, Narasimham, and Ramanamurthy, and with them was Professor Miyake, who came from Osaka City University to participate in this experiment. And what they are doing that time is using a GM counter array. It is the GM counter at the middle, and on the top and bottom are scintillator coincidence. The top scintillator is by 2 photomultiplier, and bottom is 2 photomultiplier. The coincidence will give them the muon rate, and then they take it test detector underground at different depth and measuring the number of pulses. So this is the experiment, and actually this give you many depth. Actually, they gave. I mean, they just map the whole, almost whole Earth, I would say. So from up to something like 2.7 kilometer depth that they went, and they are measuring the intensity. And at that 2.7 kilometer depth, when they reach there, which is equivalent to 8.4 kilometer of water, okay, deep water, when they reach there, and they were running that experiment, and there was no count. And all these guys, Narasimham tells me that they got tired. They just came back and told the scientific assistant who was there that if you find any count, then you send me a postcard. And they were in Bombay waiting for a postcard. That next 2 months, no postcard came. And after 2 months, they decided to celebrate. And they went to the Kalaghora and had some good dinner because they have not seen anything. And that's what I told you, that this is the MNR null experiment. They have not seen anything. They have not seen anything is the most important statement. And because this is the depth intensity curve they can measure up to many, intensity was decreasing by many orders. And then this is the depth they are going. And finally here, no count here, actually. Okay. So they realize that they have now reached a place where they can do low background experiment like neutrino. So Menon, Ramanamurthy, before they published their result, Menon, Ramanamurthy, and Srikantan and Miyake, they published a paper in 1963 saying that we have found the ideal place for carrying out experiment to study cosmic neutrinos, improve the lower limit on photon lifetime, which at that time was 10 to the power 26 years, and to prove the existence of intermediate vector boson, the predicted mediator of weak nuclear force. So these are the kind of ideas they had suggested in that paper and told that we can do that experiment. And this paper started the ball rolling for a series of experiments at Kolar Goldfield over the next 30 years to study neutrinos and the baryon non-conservation. And Miyake, Narasimham, and Ramanamurthy, that is the MNR, they actually published their paper just a little later, 1964. And when this thing is going on, there is a strong competition for the neutrino experiment. And that time, 1963, the Jaipur Cosmic Ray Conference took place. The International Cosmic Ray Conference came to India. Many stalwarts came here. Here, Cecil Powell talking to Nehru after dinner, and here Baba and Menon in the dais. So in that conference, Ramanamurthy presented this muon depth intensity result from KGF and shows that we have found a place. M.G.K. Menon discussed the plan for setting up the neutrino experiment, and also Frederick Reines, who already discovered neutrinos, he actually discussed the plan of setting up neutrino experiment in South African mine. Actually, Frederick Reines wanted to start his experiment on Kolar Goldfield, but that's a different story. I'll tell you in another day. Okay, so proposal for direct, that's how the Tata Dadam Osaka City collaboration came into existence. And Arnold Wolfendal was a good friend of Menon also. He and his group from Dadam University and Miyake's group from Osaka City University joined the experiment. It was already known by that time that the high energy cosmic ray particles interact in the Earth's atmosphere and produce pions and kaons, and those pions decay and produce neutrinos. And in Soviet Union, those days Soviet Union, Jetstapin and Kuzmin, they have already calculated the flux of those muons, their angular distribution, so you know the intensity of these neutrinos. And then 1962, this is the Lederman and Steinbacher and Melchor. They have done this experiment where they have detected muon neutrino as a separate species than electron neutrino and measured their cross-section to be around 10 to the power minus 38 centimeters square. So all these inputs, the flux, the cross-section, everything was available to KGF group. They quickly estimated the expected rate of neutrino interaction underground and optimized the size and shape of the detector that is needed to detect these neutrinos immediately. And a long tunnel at 2.3 kilometer depth at the Heathcote shaft in Championship mine, the picture I have shown in the beginning, was chosen as the site for the experiment. And in the next, immediately within a short time, they started not one detector, but they put this 100-meter long tunnel something like 7 detectors actually of different shapes and size and different purpose. And there are 3 different kinds. This is, I pick up not so good picture from Narsimham thesis. And this is actually, it's called, first was this telescope. This has actually, neon flash tube. Neon flash tube is 1 centimeter tube, long tube, glass tube, and there will be low pressure neon gas will be there. When the charged particle will go, it will flash because of the high voltage applied. And then you can have a camera in the front and you can take picture. And if you put this neon flash tube next to each other, many of them stacked to each other, then you can get a track. Okay, and then you can connect those tracks to find out the track of this. So these actually are the neon flash tube here, and these are the lead plates in the middle, so that low energy particles will not disturb them, gamma rays and so on. So this is how they were, and then these two, they have the and here we have a magnet also in the middle. This is the magnet. That magnet came from Osaka City University group, and this is to measure the momentum of the particle. So they have all these series of experiments operational by beginning of 1965 itself, and they were rewarded very quickly, and they found the first neutrino event. Now you can see the picture probably, that neon flash tube. These are round. This one is a neon flash tube, and the particles is going. This is the picture. So this is the detector. So these are the neon flash tube trays. These are the lead plates, as I told you, and scintillators both sides to trigger. And then when the particle is going at that depth, 2.7 kilometer, 3 kilometer depth, and at that angle, almost horizontal, there is no way the neon from the surface can come and mimic this event. This has to be created locally by the neutrinos and producing this neon. And this is the first event that was actually published on the Independence Day, 15th August, in the physics letter on 1965. I call it Independence Day gift by the TIFR scientists to the nation. And after just 2 weeks after this present publication, Fred Reiners published his result from South African mine in PRL actually. So the Indian group beat him by 2 weeks actually. So much was the competition in those days. Okay, so this is how. So now, importance of KGF neutrino experiment. Study of neutrinos underground became an important area of research in the field of particle physics around the world later, and several Nobel Prize winning discoveries were made using neutrinos underground. Even today, atmospheric neutrinos remain an exciting area of research in particle physics, and we propose such an experiment. Not only that, actually, so they are detecting neutrinos. Now, they realize that not necessary that all the neutrinos will be created from the atmospheric neutrinos interacting in the rock. Many of these neutrinos may be coming straight from some sources. So they are starting also looking. So they actually, what they did, they're simple. They point back those neutrinos even to the sky and see what they are coming from. Of course, I don't think they expected any miracle to happen, because their numbers was only a handful of neutrinos they measured. But they established that a process by which neutrino astronomy can be started. And this is, I would call it, the beginning of neutrino astronomy. And today, a huge detector, 1 kilometer cube detector at South Pole is doing only that, neutrino astronomy. And multi-messenger astronomy that we talk today is actually, for neutrinos is playing a part. And TIFR already published their result and in early days. And so I call it the start of neutrino astronomy. There are some other events like polar event, puzzle event was detected there, which even today need explanation. There's something like some heavy particles is decaying in the air, in the gap between rock and the detector, and giving rise to this thing. And there was excitement in the 70s, and even Sally Glasso wrote papers on this one. And there was a famous paper by Rajsekaran and KVL Sharma also on this one in Pramana. So now, after this experiment, this comes the era of 70s, and this is the era of grand unified theory. In the early 70s, Georgi and Glasso, and at the same time, Abdus Salam and Jogeshpati, they have their theories of combining the 3 forces, the strong, weak, and electromagnetic, into single forces. And as a consequence of that, photon will decay. And that's what he said. Sally Glasso made the statement, diamonds are not forever, they will all decay. Okay, and it's a grand unified theory and photon decay. So strong, weak, and electromagnetic theory, I mean, coming from a strong one single gauge forces at large symptom. A consequence of that, you can put the quark and the leptons in the same multiplet, and they can be exchanged to each other through some gauge bosons at very heavy energy, mass of the order 10 to the 16 or so. And then if that happens, then the proton can get converted into a positron and a pi 0. Okay, so proton will be sitting there and will be there. So it's just a simple experiment. You just collect a large number of protons and just wait there, let them decay, and you just record the decay product. That's all you have to do. And that's what the Indian group, that Kolar Goldfield, along with the Japanese colleagues, they tried to do in the late 70s. And what they're doing, and this is my colleagues, Krishna Swamy, Narasimham, they're all busy, testing those proportional counter that will be used. Not one or two proportional counter. The first experiment was 100-ton detector. It needed actually 1600 proportional counter of size 4 meter or 6 meter. Each of them were built not here, even in our workshop, at Kolar Goldfield itself, just in the lab there. So, so that's what we are testing there. All these proportional counter that were built here, and then slowly we built up. And that time I have joined already the group, and we started building layer by layer the stack of proportional counter, and in between iron plate, and build the detector slowly. Okay, and then when we finish, this is what it will look like, the complete detector, the stack of proportional counter X and Y direction, and looking at this, the electronics here, or the amplifier and put, but the electronics lab was very huge, because all these 16,000 channel of electronic had to become, and then they have discriminated, recorded, and so on. So all electronics, everything was built actually at Kolar Goldfield by our engineer, by scientific officer, by technician, was stationed at that point. And then, of course, another much bigger detector of something like 300 ton was built, called phase 2, and these two operational till 1992. That's some of the beautiful neutrino event. This neutrino event was going, upward going neutrino event in the detector, how they will look like. And here is what you can see, the atmospheric muons is going down. This is the atmospheric muon component, and if you go below, say something like 55 degree zenith angle, you will get only another component. These are all neutrino events. You have to tell that one. So physics studies push the proton lifetime to 10⁻31 years. New limits on magnetic monopole flux studies of neutrinos are some of the basic things that were done. And the people who are involved in that one, Krishna Swamy, Menon, Narasimham, Mondal, Srikant, and Sasi Dugar. I'm not, I mean, there were students, I'm only putting the names who are here for faculty here, just because otherwise it will be too big. Okay, so end of road for KGF experiment. The KGF experiment, which rode piggyback on the mining activities, had to finally close down when mines themselves closed down in 1992. This was final. So I think this was to go. A glorious chapter of cutting-edge experimental particle physics research in India using in-house facilities and technologies got ended. Now let me come to this very high energy gamma ray astronomy that I was going to talk about. So far I have talked about the charge component, the proton and heavier elements in the cosmic rays, but already there was in the 60s, it is known that there are sources of very high energy gamma rays. And these high energy gamma rays, what they will do, they will come to our atmosphere and they produce electromagnetic shower. Gamma rays will produce, electron positron pair, and then they will produce further gamma rays and so on. So quickly electromagnetic shower will be produced, but this will be unlike the air shower picture that I have shown, which is much broad, much spread out. This will be very concentrated, but these electrons actually will produce Cherenkov radiation in the atmosphere. Okay, and this Cherenkov radiation can be detected at by putting detectors at the surface, and can be looked for such sources in the sky. And this was started in the very beginning, very exploratory, I would say. 2-mirror system was set up in UT in 1969, and just using the Watt surplus mirror that was available, and they put it up quickly, and then they set up this experiment. Of course, this experiment was just put some limit, didn't go much beyond that. But soon they expanded that array in the 70s, 8 large and 12 small mirror array at UT in 1977 started, and they shifted because UT they ran it for few years and looked some sources, and then because UT was not so good for doing such research, because most of the nights you have to do is cloudy in UT, and also the lights all around was increasing every day in UT. So they decided to find a new place, and they moved the whole array to Panchmari during mid-80s actually, and then a bigger array with 168 mirrors, all built 168 mirrors. Now these mirrors are all built at BRC facilities, and then they are all aluminized at the Thane actually in a private company, and that's how was built all of them. And they are set up at Panchmari during mid-90s. So Panchmari they went in mid-80s, but this bigger setup with 168 mirrors came in mid-90s, and then finally they moved it to the what you call the Haggard. So this array at Hanle and started in 2008. This is a beautiful site at if you know the Hanle where the optical telescope is located. This also is located there, and this is 7 stations. Each of them has 7 mirrors and beautifully packed. Many sources and many. I'm not going to talk about the physics, and that you can talk to the individual thing. And the people, the first exploratory work was done by this group of physicists, Chatterjee, Murthy, Ramanamurthy, Srikantan, and Tonwar, and later on Acharya, Bhatt, Varsachitni, Gupta, Vishwanath, they participated in this experiment here, and Pachmari as well as in Hanle. And as you know, this field has grown up from there, and in Hanle now we have the big imaging telescope, which is running as a collaboration of the BRC, TIFR, and other institutions, IIA, and so on. Okay, so now let me move from the cosmic rays, from cosmic rays to particle accelerator. And again, it was in 60s that M.G.K. Menon and William Owen Locke. William Owen Locke, he became the leader of the third nuclear emulsion group. But there's history. William Owen Locke was the co-graduate student with Menon at Bristol in the lab of Cecil Powell. So they're good. So when Locke became the leader of the nuclear emulsion group in the early 60s, Menon immediately contacted him, and then that's how they started the collaboration between TIFR and CERN first in emulsion chambers, and then so during the early 60s, TIFR was involved in the analysis, in the only analysis of nuclear emulsion exposed to beams of ions and photons at CERN. But then the emulsion was coming to an end, era of emulsion, and bubble chamber was coming up. So TIFR decided to go establish a bubble chamber group, and then some of the physics highlight in those days are the production and decay properties of hypernuclei using emulsion, study of this antiproton proton-antiproton interaction using Sackley bubble chamber. This is the large European bubble chamber with the European hybrid spectrometer to study production and decay properties of charm particles. There are many papers they published in those days, and many people actually participated from there. Ganguly, Guttu, Malhotra, Subramaniam, Raghavan, Rangaswamy, N.K. Rao, he was in TIFR at that time. M.S. Swamy, who moved later to Aligarh University, Muslim University, he was in TIFR. So these are the people who are involved in this bubble chamber days. And in fact, Daniel also has a paper. On one paper, I know that in the emulsion era, but I don't know how much he was involved actually. Well, then really came the L3 experiment, LAP experiment in the 80s at CERN, and that is the time TIFR went there full play. So TIFR is always known for its instrumentation development. So this time TIFR, not using the data, but decided to put detector there. So this fabricated the glass tube proportional chamber for the hadron calorimeter NCAP with the Aachen group, and Suresh Tonwar played a big role in that one, in building those brass proportional counters in TIFR, using his earlier experience in instrumentation, and the significant role in the software development that time of this one. Sunanda was in charge of the software experiment. That is almost, we are now in our era. So TIFR was responsible fully for this L3 Z line shape fit and analysis over the entire left 100 period. Well, I'll tell you what that would mean. Actually, it means a lot. And the precision determinants of Z mass, widths, and coupling of distinct spaces. I'll come to that picture, then we'll know. Then also strong contribution in B physics using neural network. Neural network and AI and things like that is the buzzword these days. But TIFR scientists have started in the late 80s already using neural network for analyzing of the data. The quantum chromodynamic Higgs searches was continuing, and then the energy was increased from the energy was increased from 100 GeV to 200 GeV, and for measuring the W mass and so on and physics. So this is what I'm talking, the line shape. See, once the LAP was running, E plus E minus was colliding in the Z peak. So they can scan the Z peak from the Z peak was at 91 GeV, but you scan from 88 GeV to 94 GeV to get the whole spectrum. This is the resonant projection of Z. And studying the shape of this line shape, they can estimate or extract the parameters of the standard model. In fact, this analysis was put the standard model on the strong footing, and that was the main contribution of the TIFR group that time. And in fact, Atul Gupta even today is a part of the particle data group, and the standard model for Z mass, top cost mass, Higgs mass, strong coupling constant, and so on. And many people are involved in that time study Sunando, Somnath, Atul, Prince Malhotra, Raghavan, Sudhakar, Tolwar, Mojumdar. This is Kajori, Govindo, Gogan Mohanty, and so on. And many other students, of course. And so TIFR and D0, we joined in 1990 because the closure of the KGF group decided to have some of their own. So we decided in 1990, participated in the design and center muon scintillator. We have, from the beginning, we should contribute detectors. So we built the muon scintillator detector and fabricated 120 muon scintillator detector using help of BRC and TIFR facilities and performance studies, online studies, all voltage. This is one of our students is building those, scintillator fiber detector for the muon detector. And these are the detectors that we have built. In fact, if you have visitors is to go to see D0, they will see our detectors only because this is the outermost layer. And this plays a very good role because the muon timing was very important from background. And so they put this detector, we put this detector over there. In the physics also, we are involved in top physics, supersymmetry, leptoquark, composite, sector dimension. 8 TIFR students received PhD through their participation in digital experiment. So the people that participated here, Acharya, Sudeshna Banerjee, Shashi Dugan, Krishna Swami, Mondal, Natsimam, Srinivas Rao, Vishwanath, or the main participation from TIFR side. Now, I have now given you some idea what was this film was in TIFR. Now let's look into the future. So TIFR has a glorious past in the area of quantum energy physics. You will agree with me after seeing those slides. Several pioneering experiments were performed using indigenously developed technology, tools, and detectors. Very good. While the size of the group has shrunk, I think our group is very small. I was shouting here for almost 15 years that these groups are disappearing, but now look, they are disappearing. But it is heartening to note that the current members of the group are holding on to the tradition, at least to some extent. The UT Earth-hour array is running continuously from 1960 onward, and now you can see the real Earth-hour array, how big it is from that original one. Onward, in different shapes and size, breaking new ground and making discoveries in new areas. You all know that. The CMS experiment at CERN, where TIFR groups have made major hardware as well as software contribution, has made fundamental discoveries. TIFR has also made hardware contribution to the Bell 2 experiment at KEK. Looking forward to new discoveries there too. It is, however, not clear if ion-OICAL experiment, the largest fully funded basic science project conceived and designed mostly at TIFR, will ever see light at the end of the tunnel. I am not sure. I'm not so hopeful. So our field allows students, engineers, scientists to put their head together and develop technologies and tools before even starting the experiment. You have seen that you have developed all those things. This is a great learning experience for students and engineers who will go through this drilling exercise, will be better equipped to face the new technological challenges of the emerging world. TIFR was the only institute in the country to take up such projects from inception and convert them into real experiments. That in many fields, not only in our. Will TIFR abandon this path? I leave it to the current generation to ponder over this.